So we have about 10 minutes for Q&A with our speakers, and anybody can raise their hand and ask a question. And I know that everybody is eager to ask a question and will raise their hands quickly. Are there any questions? Yes, please.
Great talks. Thank you all very much. My question is particularly to Dr. Rohit Karnik. You mentioned that these resins actually pick up the heavy metal ions from the water for detection purposes. Have you thought about using them for cleaning? Ultimately, if they pick up so much of the heavy metals, can they be used in larger quantities to actually clean the water?
So actually, they were developed for that purpose. And so they are used in various processes for cleaning. And what we are doing here is switching their use. So rather than use them in large quantities for cleaning, we screened different of these kinds of materials available and found that some of these, which are developed for cleaning, can actually be switched to be used in small quantities for monitoring.
Thanks.
So another question.
I was fascinated by the interaction of your micelles with the bacteria. How selective are these? When you had Salmonella enteritidis and Typhimurium, kind of differentiate between E. coli and Salmonella? Do you have any idea?
Yes. Well, so we're integrating recognition elements onto these droplets. So the simplest one, kind of broad spectrum, is carbohydrate, which will not be probably selective enough. But you almost can think of it as bait to start binding things to the surfaces. But what we've done is used antibodies right now, but we can also we're also interested in using it came up earlier, Hadley's like engineered proteins, for example. She's collaborating with Brad Olson, but also she's collaborating with us on this also.
Thank you.
Another question. Yes, up in the back.
We heard from Tim and Rohit to different degrees about how the technology development was driven by user needs and constraints. Can you say just a little bit more through the course of research and development and then potential commercialization and scale up, how user considerations factor into your work and the challenge?
Yes, well, thanks, Renee, for that question. Yes, I mean, we think a lot about that. One of the, it's always like the real world is out there. We really need to start thinking about more and more as to what people want. And so all the infrastructure around MIT, basically customer discovery and such, we've made use of that. Venture mentoring service, as well as ICOR programs. But for us, I think a big issue is to figure out sampling. So one of the things about sensing, we haven't heard really a lot about it, but is sampling. How do you actually get your samples and get them intact or in a way that you can analyze them properly? And that's, I would say, right now, probably our number one challenge we're thinking about. And developing we're going to do a field trip to do a detection with under USDA supervision to see, learn from them how they think you should do sampling, how do they do it routinely, and do that. So that's a big part that we're getting from customers as to, how are you going to implement it, and sampling is a big part of that.
Yeah, so we had quite an interesting learning experience, and in the beginning we started looking at, or we went in with the hypothesis that this kind of a paradigm of being able to store the water sample in a dry or compact form, it has to have some use, but we didn't exactly know what. And we were thinking that bacterial contamination is probably where that use would be, because the volumes are larger. And so we actually went and looked at how things worked in real labs that do water testing. And what we found is that there's different people responsible for different tasks, and there is a difficulty in getting these water samples to the local lab, but that's maybe like 10 miles or 5 miles. And where it is a little bit of a hassle, it's something that is being done and it's doable. And so that kind of, we set that aside. The other thing we are also looking at is today, indicator organisms are what are tested, like E. coli are indicator of contamination, but it doesn't really tell you whether there's pathogenic microbes in the water. And what we found is that to do that, you would need to have nucleic acid analysis capabilities, and that infrastructure just didn't exist. So today, being able to preserve organisms, maybe that's possible, but then downstream, what do you do with it? That maybe is not going to happen for several years. So that we put at a lower priority. And then what we really found is that the instruments that are required for trace contaminants, those tend to be mass specs or optical emission spectroscopy. And the Pollution Control Board actually has a list of like 80 contaminants or something like that. But what local labs measure can range from as few as 4 to 6 contaminants to a max of 18 contaminants. And they are done by titration, voltammetry, and things like that. So very expensive, but the scale doesn't make sense for having like a 200K instrument, because those many samples are not available. The infrastructure and the trained people distributing so many of them is not possible. But these instruments can be put in centralized labs. And then if we somehow find a way to channel these samples to these centralized instruments, you could have a $500,000 instrument that runs maybe tens of thousands of samples, and that makes it cost effective. So that's where we saw the opportunity, and also that connection was missing. And in fact, just an anecdote, we were talking to one district engineer who is responsible for the water infrastructure. And while we were talking to him, he got a text message saying, a private company wanted to use a public source. They tested the water and they found very high levels of mercury. But testing for mercury is not very much in the capability of these local labs. So a lot of things can go under the radar, and that's really where we saw the opportunity. And so the two major classes of contaminants that emerged were heavy metals and organics. And organics technologically is more of a challenge. And so we went with heavy metals as the first focus.
Yeah, so when it comes to biosensing, a lot of people would ask, like, how do they actually beat electronics? So the reality is they can't. So what's good about biosensors right now is like they can actually operate at very low energy cost, and they're actually pretty cheap, and they can self-propagate. But other than that, the major challenge is like they are not specific enough and they are not sensitive enough. So these are like why there are like so few real biosensor like applications in the market right now. So we're still working on that, and I believe with like the recent advancement in like genetic like mutation or this kind of like optimization techniques, we can still like push forward the boundary. And the second thing is like we really cared about the safety issue, because anything that has a living component inside will be so difficult to get approved by EPA or like FDA. And like, so partially use like some proteins or like anything from the biological system without the entire living cell would be like actually a more practical solution as of now. So what we did in our work is we are trying to like use two different strategies in parallel, like the physical containment and the chemical containment in combine, and we can show like we have zero escape. So I think that's the major challenge we have. Like we want to ensure there's like zero chance of any of this engineered microbe to escape into the environment.
To make sure it's on. I'd like to thank all of our speakers, and thank you all for listening.